Hello, welcome to all. My name is Dr. Neeraj Kumar Mishra. Today lecture I am going to discuss practical quantum circuit visualization using Qiskit and Graphviz. So in this lecture I am trying to discuss these all subtopics. First is how to design DAG graph in Qiskit using Qiskit, and how to form a codes and how to install this Graphviz, and how to test quantum circuits in Qiskit and further visualize this graph using a quantum circuits, and some practical objective questions. So let's move now. So the agenda of this lecture is Python Graphviz binding in a Jupyter notebook. So what is DAG? DAG is a directed acyclic graph. So what is the meaning of directed? So directed means it is a time and ordered manner. It is a time and ordered manner approach. And we know the acyclic means there is no feedback in a design. Okay, there is no feedback or a loop, or we can say it is a loop. So in this DAG graph we have two things. One is a node. So node represent the quantum operations. Okay, so every nodes have performed some operations, and the edge which is used in a DAG, which is used for dependency between two operations. Okay, dependencies between two operations. Okay, so we are using this DAG graph, and we can visualize how the quantum circuits look in a graphical way. So in this way, first we have to use a Qiskit tool, and using Qiskit tool we can design a directed acyclic graph, and it is possible. Yes, it is possible using Qiskit. So first thing, what is quantum circuits? So quantum circuits are linear. Why it is linear? Because it is a time ordered based, and all the quantum circuits use a unitary operations. Okay, so of course the quantum operation which based on the qubits. So qubit is a information unit. So all the quantum operation based on the qubit and executed in a parallel. So every quantum operations use a superposition property. So superposition hold a linear transformation. So what is a linear transformation? Means suppose that U is that and one alpha and this kit 0, and similarly the kit 1. So this is the linear transformation, and it is equal to like this U, not U, it is alpha and U kit 0 and plus beta and U and kit 1. So superposition use linear transformation, and all the informations during the quantum state is superposition, and all the measurements, if we measure the information, then superposition property destroy, and that is a classical information. So after measurement, quantum evolution stops. Okay, now how to use a Qiskit in our platform, maybe Jupyter or maybe PyCharm or maybe Google Colab or any other Python tool. So first thing, we need some essential bindings. We have to do the installation process. So we have to run all these installations in our local platform, maybe Jupyter. So we have to run all these things. Then if the whole Qiskit binding with the kernel of a Python, then we can execute our quantum circuits. Okay, so now our agenda is we have to design a DAG graph for any quantum circuits. So we are using a Graphviz in a Jupyter notebook. So the essential requirement is we have to use this Graphviz, and this binding is also required in the local platform, that is Jupyter. So first we have to do the fundamental things to include this Graphviz package in a Jupyter notebook. So one means the process is very easy. We have to run this code in a Jupyter notebook. So that is the installation process. And if we use the Conda, so Conda is a software package. We know the Conda is a software package, and it creates a isolation environment. Okay, so these means if you have a different projects, and each project have a different version of Python platform, and many libraries files are there, so there is no conflict. If we use Conda, there is no conflict in different library files. So in this way we can use this command. Okay, or any other way is we can manually have to install this Graphviz by clicking on this website, and make sure your environment is created in a environmental variable. So how you can verify this thing? So just put a window plus R. Okay, if you press the window R, then the run command will be open. Then we have to, okay, I will show the practical way how to verify this package is installed properly. You just click on window R and just run this sys dm.cpl, and if you click on this, okay, so this system property will open, and click on this advanced option and go to the environmental variable, and go to the system variable and create a new environment. And we have to show that our package is if not installed, if the variable path is not installed, so we have to run this command. Okay, we have to run this. Okay, we have to type here properly. Okay, and then you click OK. But in my system it is already there variable, so I cannot do now. Okay, so there are this is a manual approach. We can install the Python Graphviz package in a Jupyter notebook. Okay, so do not forget to reinstall or relaunch the kernel. Okay, means if you install the package, so you have to must sure that you must restart your kernel to execute the code. Okay, so this is installation process. I already tell you, just press this window R and type here and go to the environmental variable and go to the system variable and click on the new, and make sure that this path is available in your system environment. Okay, so if you satisfied that this environment is already created, then you have to go to the Jupyter notebook and install the working on that. So in this slide I'm just going to discuss about the fundamental things, how you create a node and how to create each between two nodes. So first we have import this Graphviz class. Okay, this is a class which is from the Graphviz Python package, and we are using this command. So this command is create empty directory directed graph objects, and that is stored here. Okay, that is stored here, and during this object store, okay, if we have a store of objects, so there are three things. One is the node, what is your node, and what is your directed each. Okay, what is your directed is, and later you have to define your layout. Okay, graph attributes. Okay, I just write here graph attributes. Okay, so graph attributes is your layout or labels. Okay, so I'm using this node. This is my node A, and this line denotes we are creating a node B, and we are stabilizing a connection between these two nodes, and this is our source node. Okay, and this is our destination node. Okay, so if we run here, we can see this is a graph. Now, how the quantum circuits, okay, how the quantum circuits are designed in a Qiskit, and how to design a DAG graph. Okay, so in this slide, I'm going to discuss this two part, the circuit part and also the visualization of this DAG graph. So first you import this Qiskit library files and import this converter. Okay, means circuit to DAG. DAG is a directed acyclic graph, and we have mentioned that there is a 2 qubit gate, Q0 and Q1. That's why it is mentioned 2. 2 means one is qubit is Q0 and second one is Q1. And we are going to design a circuit that is QX, CX. CX means it denotes a control NOT gate. In control NOT gate, there is a one dot and one is target point. Okay, so you can see here, this is the CX gate. Okay, so after that we have to draw quantum draw a DAG diagram. If we execute here, we can visualize this quantum circuits. So let's move to the Jupyter notebook, and we can see how this thing is practically possible in a Jupyter notebook. So you can see here I written the very much similar code which I presented in my slide, and I tell you, this is my quantum circuits Qiskit importing a library files, again importing from circuit to DAG graph, and in this line I am just saying that the quantum circuit have two wires, that is quantum wires, and in this two wire, one is I am using CX gate, and one 0 represent the target control point, and the 1 represent the target gate. And I measure all the lines in all the there are two lines, so we have to measure all the lines, and then we draw this DAG graph and store here, and then we have to plot here. So I'm going to run here. So now the Qiskit is going to implement a DAG graph. Now within few seconds we can see this graph is visualized here. So you can see here the Q0 and Q1 two qubits in which is implemented on a CX gate, and there is a barrier, and after the barrier there are two measurements line, and you can see in after the barrier we are measuring a qubit 0 and qubit 1. So this is a structural approach how the quantum circuits process in a graphical manner. So that is a good visualization of a quantum circuits. So let's move to implement more quantum circuits in a Jupyter notebook with DAG graph. So in this slide, I'm going to discuss another gate, quantum gate, that is CCX gate, which is known as a control NOT gate. In this control NOT gate, there is a two control point. This is a control point, and this is a target. Okay, these three are the measurement lines. Okay, these three are the measurement lines, and so if we have three wires, so we have to mention here 3, which is represent, these are the qubits, and this is the syntax for CCX gate. And if we run here, we can see the visualization of a DAG graph, which is the correct view of a quantum circuits. So let's move. We have to implement this CCX gate with DAG diagram in a Jupyter notebook. So this is the code. Same thing. I just type here, and if we run here, so now the Qiskit is going to implement this DAG graph. You can see here there are 3 quantum circuits, Q0, Q1 and Q2, which is going to the CX gate, and there are 3 measurement lines, and after that 3 measurement lines we can measure the qubits, okay, by measuring line, by measurement line. Q measure 0, measure 1, measure 2. Okay, now we are more interested to implement a more quantum circuits in a Qiskit, and also we are interested to make a graphical directed acyclic graph for other quantum circuits. Now there is a very famous gate, that is swap gate, which is also very popular in a quantum world, like a multiplexer. Okay, so here I'm using all this line is same, okay, but this thing I written here 2 means there is a 2 quantum qubits, and I use this swap. Swap is a keyword of a Fredkin gate. So you can see here, if we run this is a quantum circuit, and this is a DAG graph. So that is a visualization here. So the same thing I implemented in a Jupyter notebook, and if we run this code here, now we can see the correct visualization of a quantum circuits using a Qiskit, using a Jupyter notebook. Now you can see this is a graph for a swap gate. Okay, so let's move to a more complicated circuits like Bell state. So we know the Bell state is very much popular in a quantum world because it is used for many applications like quantum teleportations and quantum cryptography and super dense coding, and also the quantum networking. So quantum networking basically use a entanglement distributions. So these are the very basic application of a quantum of a Bell state. So Bell state is a combination of 2 gates. One is H, another one is CX gate. So this is a visualization of a quantum circuits of Bell state. Now we are going to use this 2 line to represent a Bell state. So the first line represent the Hadamard gate, which is on first qubit line, first quantum line, and another one is CX gate, which is available here, and it is using a qubit 0 and qubit 1. So qubit 0, Q0 represent a control point, and this Q1 represent a target gate. Okay, so we have used this line only because we have already imported this Graphviz in a Qiskit. Then we can easily view our DAG graph. Okay, so you can visualize here. We have used the 2 gate. One is H gate, which is connected to a qubit 1, and CX gate, which is associated with Hadamard gate and also the qubit 1. You can see here it is this line, CX gate line is associated with H and also the Q1. So that is showing here. Okay, that graph is showing here properly. So we can see here after means after the barrier, this is a barrier, and after the barrier we are using a measurement line. Okay, so these are the measurement. So we have measured a qubit Q0 and Q1. So I hope this visualization of DAG graph is very much understand you here. So let's move to do some practical questions, which is very helpful to check our knowledge. So I've given you one question is in Qiskit, the function, this is a function, what is the use of primary, what is the use of this function. So these are the options. Okay, these are the options. So I give you some time, you can think about this practice questions. Okay, so I hope you have completed this task. So you can see here the C option is correct. So this C option is convert a quantum circuit into a directed acyclic graph. So directed acyclic graph is a time and ordered manner, and it is a no loop feedback concept. Okay. Now, in which of the following, next question, which of the following statement about Qiskit DAG circuit is true? So these are the options. So I hope you have think about the option which is correct. Now this C option is correct because DAG circuit represent gates and nodes and the execution order because we know the DAG gate using a node, okay, and the directed is and a graph attributes. Okay, so this C option is correct. So thank you very much to all to see in this video lecture which is related to quantum circuits and the DAG graph. Thank you to all.